So today we shall be covering one of the most popular and most used algorithm in CP. So that is binary search. So binary search is, as I said, one of the most used algorithms. And as the name suggests, it is a way of searching. And it is applied under a certain special circumstances. And in those circumstances, it turns out to be a very special, very efficient way of searching. And as you can see, the time complexity is less than O(n). So broadly speaking, it can be classified into two types: binary search on an array and binary search on a range of possible values. Let us begin with binary search on array. So let us understand this to the problem. Now consider this array which is sorted. Now our job is to um, find the index of element 6, and the indexing starts from 1. So basically the index of first element is 1 and not 0. Index of this is 2 and so on. Index of 8 is 6. So we have to find the index of 6. How do we do that? The naive approach is to start from the first element and iterate through the array until we find the required element. Then when we find the required element, we break from the array and we output that value. So basically here IDX is an integer variable. So int I equal to 0, I less than 6, I plus plus. So here we are iterating through the array. And when we find the required value, when array I turns out to be a required value, which is 6, uh, we assign it to IDX. So basically here I is in the 0-based indexing format. So in order to convert it to 1-based indexing format, we add 1 to it and we assign that to IDX, and then we break from the loop, and then IDX is a required answer. So, and in the worst case is when our required value is the last element in the array. So in that case, we'll have to iterate through the entire array. So it has linear time complexity over time. So, and what is the binary search approach? The binary search approach, we introduce three variables: start, mid, and end. So start is the index of first element, end is the index of last element, and mid is the average of start and end. So when our array's size is odd, mid is the index of middle element, and when the size of array is even, mid is one of the two middle elements, index of one of the two middle elements. So now here we'll iterate through a loop as long as start is less than or equal to end. And if start becomes greater than end, we'll exit the loop. So now if array mid, the value of array at mid is less than the value that we are searching for, we'll make end as mid minus 1 and then update mid with the average of the start and the new end, the modified value of end. Otherwise, if array mid is less than the value that we are searching for, we make start as mid plus 1 and then again update mid with the average of start and end. If array mid is equal to the value that we are searching for, we exit the loop since we have found our value, and mid is our required index at which our value is present. So let us understand this through this. So this is the array that we have seen previously. So initially our start is 1 and end is 6. Start is the index of first element 1 and end is the index of last element, which is 6. So mid is the average of start and end. So 1 plus 6 by 2, 3.5. And if we apply the greatest integer function on it, we get 3. So now array mid, which is the value of array at index 3, which is 3, is less than 6. So start will become mid plus 1. And now start mid is 3. So start becomes mid plus 1, 4. And start is less than end, which is 6. So we still continue iterating in the loop. And then start becomes 4, end becomes 6, and mid will be the average of start and end, 4 plus 6 by 2, which is 5. So now since our array mid is 6, we'll break from the loop, and mid, which is 5, is our required answer. Now I have a question. So what happens? So here we were searching for 6. Now let's say what happens if I search for an element which is not present in the array and is greater than all the elements in the array. Say let's say we search for 9. 9 is not present in the array clearly and is greater than all the elements of the array. So what happens in that case when we search for 9? Scan the QR code and answer the question. Okay, fine. So most of you got it correct. So end remains unchanged and start becomes greater than it. And why is that? Let's say we are searching for 9. Now, no matter what our mid is, our mid will always be less than the value that we are searching for. there because array mid is just an element of the array, and that will certainly be less than 9. So start will always be mid plus 1. So here what will happen? Start becomes mid plus 1. So start becomes 4, mid becomes 5, and again array mid is less than 9. So start becomes mid plus 1. So start becomes 6, and mid again becomes start plus n by 2, 6 plus 6 by 2, which is 6 again. And so since again array mid, which is 6, which is the value at index 6 is less than 9, again start becomes mid plus 1. So start becomes 9, and start becomes 7, and then remains as 6. So what happens is n remains unchanged, then start becomes greater than n. And what is the implementation of the above algorithm? So start is 0. So start is the first element, index of first element. End is 5, end is the index of last element, and mid is the average of start and end. So while start is less than or equal to end, we iterate through the array. If array mid is greater than 6, we make end as mid minus 1. Else if array mid is equal to 6, we break. Otherwise, we make start as mid plus 1. And finally, and no matter what we do, we always have to update mid with the average of start and end. And the final required answer is mid plus 1. Since mid was in the zero-based indexing format, we have to output mid plus 1 as our answer. So the time complexity of binary search is O of n. Why O of log n? So why is it O of log n? As we can see, our start and end represent the ends of the array that we are currently searching in. So every time we update either start to mid plus 1 or end to mid minus 1, so the range of array that we are searching for get the size range of array that we are searching for gets reduced to half. So let's say initially the total difference between start and end was n, it becomes n by 2. So when in the worst case, we'll have to iterate until start becomes equal to end. So in that case, when start is equal to end, the array that we are searching for, the size of array that we are searching for becomes 1. So let's say it takes x steps from the x steps for the size of array to become from n to 1. The range of array that we are searching for, let's say it takes x steps for it to become from n to 1. So since in each step the size of array gets halved, after the x steps it becomes n by 2 power x. That is 1. So 2 power x is n and x is log n to the base 2. So in the worst case, we'll have to perform log n to the base 2 steps. And I have another question. Does binary search work if the array is not sorted? We can scan the QR code and answer this question. Fine. So most of you got it correct. So it does not work if your array is not sorted. And why is it? It's because you look at the algorithm. So here, when array mid is greater than the value that you're searching for, you'll make end as mid minus n. And why do you do that? Now, since your array is sorted, all the elements lying to the left of mid will be less than left of the index mid will be less than the value present at index mid, and the value present at index mid itself is less than the value that you're searching for. So it's clear that uh, sorry, just a second. So now if your array mid is greater than the value that you're searching for, now all the elements lying to the right of mid will be greater than since your array is sorted will be greater than array mid, and array mid in turn is greater than the value that you're searching for. So clearly your elements can't lie in the right half of the array, so you'll make end as mid minus one and search in the left half of the array. And similarly, when array mid is less than the value that you're searching for, you make start mid plus one. Since your array mid is less than the value you're searching for, and all the elements lying in the left half of the array will be less than array mid, and hence will be less than the value you're searching for. So they won't be present in the left half. So you'll search in the right half. So, and clearly, if your array is not sorted, this logic won't work. So you have to always apply binary search only when your array is sorted. So here is your attendance. So please mark it quickly till the attendance form will soon be deactivated. Fine. So let us continue. So our next topic is binary search and a range of possible values. So, and most of the problems that you would be seeing on binary search will be on this topic. You'll never be given an array and you'll never be asked, you'll never be given a sorted array and you'll never be asked to search for a certain element in the array. So most of your questions will be on this topic, and it is not really intuitive to identify problems based on this topic. So always keep this method in mind whenever you solve a problem. So let's say we are given a function f of x which returns true for the first few integers, let's say until a given integer k, and from all the integers greater than that k, it returns false. So also we know that the function returns true for 1 and it returns false for a given integer n. N is known to us. So of course the naive approach would be to iterate from 1 to n and calculate the value of function for each integer and then find the last element for which the function is true. So what is the binary search approach? So similar to the previous one, we declare three variables: start, and then start being 1 and then being n, and we declare mid, which is equal to the average of start and end. So we then calculate the value of function at mid. If it is true, if the value of function at mid is true, then we make start as mid plus 1. Previously, we were finding the value of array at index mid. Here, we calculate the value of function at mid, at the integer mid. And now if it is true, we make start as mid plus 1. Else, if it is false, we make end as mid minus 1. And then we again update mid with the average of start and end. And we iterate through the loop as long as start is less than or equal to n. So one more difference is that last time, as soon as you found out your index, as soon as you found out your array, the array at your given index is equal to the value that you're searching for, you broke out from that. But here you can't do that. You'll have to iterate as long as start is less than or equal to n. You can't break like that intermediately. And the final value of end is our answer. Previously, the final value of mid was our answer. Now it is the end. So let us understand it through this example. So here, let us take n as 6. That is, for 1, the function returns true. For 6, the function returns false. And now mid is start plus n by 2, which is 7 by 2, 3.5, and you apply the greatest integer function, it becomes 3. Now, f of 3 is false. So what do? You make end as mid minus 1. So n becomes 3 minus 1, which is 2. So n becomes 2 and start remains 1. And now your mid will again be updated with the average of start and end. So mid will be 1 plus 2 by 2, which is 3 by 2, 1.5. Step of 1.5 is 1. So mid will be 1. Start equal to mid equal to 1 and end equal to 2. So f of 1 is true. So what do? You make start as mid plus 1. So start becomes mid plus 1. So start, previously our mid was 1. So start becomes mid plus 1, 1 plus 1. So start becomes 2 and then also remains same as 2. And now your mid will be the average of start and end, which is 2 plus 2 by 2. So mid will also be 2. And now the function returns true for mid. F of 2 is true. So start becomes mid plus 1, which is 3. And now your start is no longer, so now your start becomes 3 and end becomes 2. And now your start is no longer less than or equal to end. So you break out from the loop. And now your final value of end, which is 2, becomes your answer. That is, 2 is the greatest integer for which your function returns true. So as you can see here, you're iterating as long as start is less than or equal to end. You can't uh, exit from the loop intermediate. Okay. So this is the implementation of binary search approach and the naive approach. The naive approach, what do? You declare an integer greatest in which you would be storing your required value. And now you iterate from 1 to 6. That is from 1 to at here n in our case is 6. Now fn is the name of the function. Fn I is true. You update greatest to I. Other than else, if it is false, you break. So as soon as you reach the first element for which it is false, it breaks from the loop. And as long as it is true, it keeps updating greatest with the value of 5. So finally, your greatest will be uh, the greatest value for which function returns true. Since greatest is your answer. What is the implementation of binary search approach? So your start is 1, end is 6, and mid is the average of start and end, which is 6 plus 1 by 2 turns out to be 3. So when you do by 2, it by default truncate applies the greatest integer function program. So while start is less than or equal to end, if function mid is true, you make start mid plus 1, else you make end mid minus 1, and you always, no matter whether function is true or false, you always update mid with the average of start and end. And end is our required answer. So now assume the time complexity of the function is O of m. That is to calculate the value and return the true or false. At each integer, the function takes O of m time. Assume that. So the time complexity of the naive approach will be O of m into n. Why is it O of m into n? Because in the worst case, you'll have to iterate from 1 to n. So you have to iterate through n elements, and for each element, the function takes O of m time to compute the value true or false. So the total time taken would be O of m into n. And in the binary search approach, in the worst case, you will iterate log n times, and at each value, it takes O of m time to compute true or false. So in the worst case, the time complexity will be O of m into log n. And another question, let's say your function returns true for integers 1, 3, and 5, and it returns false for 2, 4, and 6. Can we still apply the binary search approach to determine the greatest value for which function returns true? So I'll give a couple of minutes of time. You can answer this. Wait for a couple of minutes for more people to answer, and then proceed. Okay, so now let's continue. So the correct answer is no, it can't be applied. So why can't it be applied? So see, here uh, if your function, if the value of function at mid turns out to be true, you're making start as mid plus one. Why are you doing that? Because if the value of your function is true at mid, for all the elements lying to the left of mid, it will certainly be true. Because let's say uh, uh, say here mid is 2, and for mid the value of function turned out to be true. So it is certain that for all the elements to the left of mid, in this case there is only one element to the left of mid, for all the elements to the left of mid your function will certainly return true. So the greatest element for which your function returns true certainly won't lie to the left, because as you know mid itself is an element for which it is true. So at max it might be mid, or it might lie to the right of mid. It certainly won't lie to the left of mid. And similarly, if your function value turns out to be false at mid, you make end as mid minus 1. Why? Because if your function turns out to be false at mid, for all the elements to the right of mid, it will certainly be false. So let's say here your mid was at 3 and it is false. So for all the elements lying to the right of mid, it is false. So the greatest element for which it is true won't lie to the right. It will certainly lie to the left of mid. So let's say if your function returns true for alternate values and false for the rest alternate values, this monotony is missing. So if your function needs to have this kind of behavior in the return values, it needs to be monotonic. So it has to be true for the first few elements and false for the rest of the elements, or it can be false for the first few elements and true for the rest of elements. So even if this was false, false, and then true for the rest, it would work because that monotony is present. But if the monotony is not present, if it is true at random values and false at random values, this logic will no longer work. So, so therefore, in such cases, like in this case, uh, like in this case, a function was returning true for alternate values and false for alternate values. That monotony is clearly not present. So your binary search approach can't be applied for this. That's it for the session. So you can scan this QR code and share your feedback about this. Wait for a couple of minutes. So that's it for today's session. Hope you all learned something and hope you all enjoyed this session. So next we would be having a session on 2 pointers after this.
Hello, am I audible? Hello. Uh, Fine. So, hello everyone. I'm Suraj, a coordinator in the programming club. So today we'll be looking at two pointers method. It is pretty simple in implementation, but it can be tricky sometimes. So let's just look at it. Also, is my screen visible? Uh, Something in the chat box? Yes, no, a thumbs up maybe. Yeah, thank you. So first, we'll be going through the basics of two pointers, like what two pointers actually is. Then we'll be looking at when to use two pointers, some illustrations to get you pretty familiar with two pointers, some basic standard implementation problems, and later on some advanced problems which might require a little bit of thinking, but it is pretty standard, so it won't be a big issue. Yep. So let us see what two pointers are. So two pointers, as the name suggests, you are using two pointers to do some condition check over two different values. And you just iterate to the data structure on which you're doing this condition check, and you just find whatever is required. This is usually used when you're trying to implement the problem in O of n time. And as we know in competitive programming, O of n is generally the best that you can do to find an answer. So this is a pretty efficient problem in a way, in a pretty efficient approach in a way. This is just a basic representation. You are using a pointer one to do a condition check on this variable, or pointer two to do a condition check on this variable, and then you're just checking if it matches our some specific condition, and if not, you just iterate to the next element based on your requirement. So when do you use two pointers? As a general rule of thumb, it is not like a foolproof method. Like you can use two pointers here, but generally, whenever you see a problem, and if you see some patterns in the problem, you might think two pointers might be the right way here. Searching and optimization of problems. Let's say finding pairs of values in an array with sum of 2k. Generally, it would take O of n square times if you're not implementing it efficiently. But with two pointers approach, when the array is sorted, then you can do it in O of n time. We'll look at this tree in the session. Sorting and manipulation problems, like rotating an array by k steps. If you don't know what rotation is, I'll explain it to you when we reach this part. And intersection and merge problems, like merge sort. This is a pretty popular sorting algorithm, which is not generally the most efficient, but it might give you a good practice over recursion and two pointers. as you just break the array into multiple subparts, sort that array and merge both of them array and sort that array and do that recursively. I encourage you to look this up over the internet, as it is pretty interesting exercise on recursion and the two pointers approach. Okay, so let's move on to the next slide. Okay, so let's consider this problem. We're given a sorted array, sorted in the ascending order, having some n integers. We're asked to find if there exists any pair of elements ai, aj in that array such that the sum equals to some specified value x that we're giving you. So how would you implement this? Let's just hear your opinions. Something. Just type a chat box. What comes to your mind when you just think of this problem? Something? No. Yeah, I see an answer. Loop ij that we could make one variable. Okay, fine. Mapping. It might be not. It might not be very efficient to be honest. Mapping, but it is interesting to look at. Okay, right. Someone said loop ing, and obviously that is the first thing that would go to our mind. We can just set up a double loop and find a pair for each ing, but it is not very efficient. As you know, double loops, we don't prefer them in competitive programming as its time complexity is O of n square. But for those of you who are interested, this is how a double loop uh, solution would look like. We are setting the return type of this function as Boolean because we want to check if the number x is in this array and we return true if we find it. We loop through each element over the array for I0 to n. If I is equal to j, then we just continue with the next iteration because we want distinct pair of elements I and j. So we just continue. And if I plus array index I plus array index j is equal to x, we return true as we have found the element. And if it is greater than if array index I plus array index j is greater than x, then we just break because as the okay, yeah, two-pointer approach, yeah, I'll come to that, but that is the correct answer. If array index I plus array index j is greater than x, then we just break out of the loop because as the array is sorted, any element after this jth index would only increase the value of array index I plus array index j. And if we haven't returned anything from these loops, then we just return false as we haven't found any pair of sum. So pretty straightforward, right? But obviously the time complexity here is O of n square because we are using a double loop. But we can make use of the fact that this array is sorted. So what would you do? You're given that the array is sorted. Try to think of it in this way. The array is sorted and you have a hint that you have to use two pointers. What can you do? I'll wait for about a minute. You can just type it in the chat box. Uh, I don't see anything, so I'll just continue. So apply binary search logic. Um, we are finding some. Will binary search work? I think it might work. Yeah, it might work. Well, yeah, that might be an approach. Yes. Well, let me share what I thought when I got this problem. So as the array is sorted, we can initialize two pointers, a left pointer which starts at the beginning of the array and a right pointer which is at the end of the array. using the zero-based indexing. So we are setting the left pointer to be 0 and right pointer to be at n minus 1. Yeah, start and end basically. While left pointer is less than right pointer, if array index left pointer plus array index right pointer is equal to x, that means we have found a pair which equals x. We just return true. If the sum of array index left pointer and array index right pointer is less than x, then we increment left pointer because we want a sum which is greater than what we have right now. And as the array is sorted in the increasing order, uh, we just increase our left pointer so that we get a greater sum. Otherwise, we just decrement our pointers as we want a lesser sum. Right. Could anyone tell me why we are doing left pointer is less than right pointer? Why are we doing left pointer is less than right pointer? Why not left pointer is less than equal to like right pointer? I'll bring up the question again. Just take a look at the question and tell me why we are doing left pointer is less than right pointer. Right. Yes. As we want distinct pair of elements, we are doing left pointer is less than right pointer. Yep. This is what I just explained. As array is sorted, we can easily compute sum of left and right elements. Yes, yes, yes. If the sum is greater, we just reduce our pointer. If sum is smaller, then we just increase the left pointer. And if we find a sum, then we just return true. And obviously, as I stated earlier, two-pointer approach is generally O of n time complexity. So it is also O of n time complexity. Right. Everyone's clear up to this point? Or does anyone have any doubt? Um, I assume everyone is clear. Right. Let's just move on. Okay, let's look at a basic implementation of a two-pointer approach. A k rotate. Let's look at the problem. Given an array, rotate the array to the right by k steps where k is non-negative. And here I'm explaining what a rotation operation is. Let's say you have an array, this array of some integers, 1, 2, 3, 4, 5, 6, 7, and you're rotating it by 4. That means you take all the elements till the fourth index, all the elements after the fourth index, remove them, shift all the elements before the fourth index to the right, and place all the elements that you had removed to the beginning of the array without changing the order. Is that clear? What a rotation operation is? Because this is pretty important. You can just type in the chat. Yes, no. Okay. So we can solve this using double loops, or there is another approach where we can just uh, slicing. Yeah, slicing. Yeah, we can do that, but there we would have to create another array, which is not very memory efficient. Well, we don't really look for memory efficiency in competitive programming, but yeah, we want to solve it in O of n time complexity and O of one space complexity. Yes, I see some answers. Well, I'll just let others think. What would you do? So given that you have to use two pointers approach to solve it efficiently, what did you try to do? I'll just give you a hint. We have to think about reversing the array and subarrays. Does anything pop into your minds? Yeah, yeah, yep. That is correct. We reverse till k, and yeah, what you said is correct. So let us look at uh, how we would do this. Okay, let's look at the solution. As rotation is involved, we notice that every one rotation, swapping, yeah, essentially it is kind of swapping, yeah. Oh yeah, every one rotation, you see that the last element comes to the beginning of the array, right? And rotation by any k greater than one is basically rotating by one k times on the updated array each time. So we reverse the array initially to bring the last element to the beginning. Then we uh, fix the array, fix the subarray, the beginning array to get the initial last element to its correct position and the rest of the subarray elements to its correct position, and we reverse the other array. This will be more clear when we look at the example. So let's just take an example where an array is given and let's say k is 3, right? Let's say this is our initial array. Uh, the same plain old 1, 2, 3, 4, 5, 6, 7, nothing new. Okay, so this is the initial array. Now we are just reversing it. You can just reverse it using swapping, right? Reversing the array. Then as k is 3, we take the third, we take the third element, k equals 3, and reverse the subarray beginning from index 0 to this pointer, this position. So we just get this, and now we notice that this is incorrectly placed. So we just correct this by reversing this subarray, the rest of the subarray, n minus k subarray, the subarray with length n minus k, and we get our rotated array. Is that clear? This works because uh, every rotation, a rotation by k essentially is rotation by one k times on the updated array. So that is why this approach works, right? Let's just look at its implementation in code. Okay, this is my reversing function where I'm using two pointers, start and end, to reverse the elements of arrays and subarrays. It takes three parameters, input the array itself, the starting pointer and the ending pointer. And this is just standard swapping function. Then this is my rotate function, which rotates the array by k. We are taking k modulo equal to length because if k is greater than the length of the array, then we notice that a rotation by k, a rotation is cyclic in nature. So essentially, rotation of uh, k equals n is essentially rotation by 0. So we just do this for our safety, as if we get a k greater than n, then we don't want to do it again and again and waste time. So we just do this k modulo equal to length, which is essentially k equals k modulo length, and length is the length of the array. So we reverse the whole array first using this first operation. We're reversing the whole array. Then we are reversing the subarray, the first subarray from 0 to k minus 1 index. And then we are reversing the other subarray which was incorrectly positioned from index k to index length minus 1. Is this correct? Is this clear? Any doubts? You can just type in the chat. Wait, am I audible in the first place? Um, okay, yeah, fine. So I assume there are no doubts in what I just explained. So let's just move on with the next example. Is that fine? Fine. I'll just move on. Its time complexity is open, two-pointer approach. So yeah. Okay, let's look at this another problem. It is pretty interesting. So let's just see what it is. We are given an array A consisting of only zeros, ones, and twos. We want to write a function that sorts the given array uh, in the increasing order. That is, we want all the zeros to come in the beginning, then all the ones, and then all the twos. Right. Obviously, we can use the sort function in essentially every programming language, but we expect an O of n solution, whereas the sort function generally has the worst case time complexity of O of n log n. So let's think. What can we do here? Any ideas? We don't want to use the sort function. Yeah, that is what this problem essentially is. But uh, what would you do? Okay, let me just give you a hint. I lied a bit. This is not technically a two-pointer problem. It is a three-pointer problem with pointers as low, mid, and high. Can you think of something now? Binary search, uh, I don't think it is that efficient here. But okay, wait. It is in a way binary search, but not exactly. Okay, let me give you another hint. We have three pointers, right? So that divides the array into four sections, four separate sections. What would each of those sections represent? That is from zero to low, low to mid, mid to high, and high to n minus one. We have four sections in the array. Um, okay, all right. Let's just look at the solution. Um, we don't want to create a new array, and we just want to manipulate the original array. Like I forgot to mention that part, but we want to manipulate the original array. Okay, let's look at the solution. We keep three pointers. Uh, okay, it is encouraged to not post the code in the chat, as it'll be spoiled a bit. Let's look at the uh, approach first. Okay, so we keep three pointers, low, mid, and high, and there are four ranges. Zero to low, we take that range to be all the range containing all the zeros. Low to mid, the range containing all the ones in the array. Mid to high, we don't know what elements are there in that range. So those elements are yet to be evaluated. And high to n, that range contains all the twos in the array. Right. So we have these four ranges. Now what can we do? Okay, let's look at what we can do. We traverse the array until mid is less than equal to high. Here our mid is our running pointer. It is involved in all the condition checks in this problem, right? And we do that and we traverse the array until mid is less than equal to high. We know this one condition now. Like after this condition is not fulfilled, we just break out of the loop. And that would imply that we have sorted the array in increasing order, right? Now, if the element at the pointer mid is zero, okay, this is the important part. So let's pay attention here. If the element at pointer mid is zero, then swap the element with the element at index low. That is essentially a pointer low, and update low and mid by incrementing them by one. Okay, cool. Now, what if the element at mid is one? We don't do anything. We just update mid. Because remember, everything between low and mid represents one, the range containing one. So we just increment mid. We don't do anything there. And what if the, okay, let me ask you a question. What if the element at mid is two? What do you think we would do? I've given you two conditions and what we would do in each of those conditions. What if the element at the index mid is two? What would you do, logically speaking? I don't say anything, so let's just proceed as okay. Mid minus equal to one. Uh, I don't think that would do anything. No, that would not do anything because everything in the range from mid to high represents unknown elements. By decrementing mid, I don't think we are doing something useful. Swap with high, yes, yes, that is what we would do. We swap with high and update high. If element at mid is two, then swap the element with index high and just update high equals high minus one. We just decrement it by one. And as we don't know what exactly is at mid at this point, we don't do anything to mid. We just decrement high and we go on with the loop. Okay, right. This might be too much to take, but so it is pretty easy. So let's look at an example. Okay, let's just visualize. Let's say we are given this array 0, 1, 2, 0, 1, 2, right? We have initialized low and mid to 0 and high to n minus 1. That is length of array minus 1. Now here, uh, the index, the element at the index mid is 0. So what would you do? According to our algorithm, we would just swap it with low. We just use our swap function, swap it with low, and increment mid and low, right? Okay, so we just swap and increment mid and low. So swapping does nothing to this element because both are pointing to the same element. We just increment both of them. Now, element at mid is 1. In that case, we know that the range from low to mid is the range containing all the ones. So we just simply increment the pointer mid and we just move on because that's what our algorithm says. And that's what we had uh, given the meaning to the range between low and mid. Just increment the mid and move on with our next iteration. Okay, so now uh, element at mid is 2. What do you want to do? We want to swap it with the higher element, the element at the index high, and decrement high. And we precisely do that. We swap it with the element at index high. As both of these elements are 2, there is no visual change, but yeah, we have swapped it and decremented the element at index high. As we and now we continue with our loop. We still see that element at mid is 2. So we swap it again with high and decrement element at index high. So we decremented, we swapped it, and we had decremented the element, the pointer high. And later on, as element here is 1 again, we increment mid according to our algorithm. And according to the ranges that we had defined, we increment mid. Our mid reaches the element 0. And now according to our algorithm and the range that we had defined, everything between 0 and low must be all zeros. So we just swap it with element at low and increment mid and low. So we just increment mid and low, swap it with element at low first, and then increment both of them. Now here, as the pointer mid is greater than high, we just break out of the loop, and that would mean we have sorted the array. As our condition was, as long as mid is less than equal to high, we continue with this loop. Is everyone clear? Or does anyone have any doubt? Just type yes, or just type your doubt in the chat. Attendance link will be shared later in the session. I think after the slide, maybe, yeah. So no doubts about the implementation. I'll wait for another minute. Okay, I assume there are no doubts in this problem. The Dutch flag thing is essentially the name of this algorithm. Uh, so yeah, you need not worry about its name. Just focus on the implementation and the approach that we are uh, taking on. Okay, right. Let's just move on. The code would look something like this. This is just what we are. This is just implementing what I just explained. We are just initializing low, mid, and high. Array size is the length of the array. While mid is less than equal to high, we are using switch case because it just makes the code look fancier, I guess. If array index mid is 0, we swap low, mid, and increment them. If element at mid is 1, we just increment mid. And if element at uh, mid is 2, we swap first and decrement the high index, doing nothing to the element at index mid. And obviously, the time complexity of this algorithm is O of n. Okay, so this is the attendance form. Please make sure you fill it. I'll wait for about 2 minutes on this page. And in the meanwhile, if anyone has any doubts, just put them in the chat and I'll try to explain them. Yes, there is a contest on 30th June, I think. Oh, it is no longer accepting responses. Okay, just a second. Could someone from the managing team contact the form administrator, Apurva, about this issue? Uh, I'll I'll show this attendance form in the end too. So you need not worry about it. Okay, all right. Let's just move on. I'll show this form in the end too, so you don't have to worry too much about it. Okay, yeah, fine. Let's look at some advanced implementation of two pointers. This is a very famous problem. It is available all over the internet. But this is a great example of why we have to use two pointers approach. So let's just look at the problem. Given an array A where each element denotes height of blocks, calculate the total volume of water that can be trapped when it rains. Okay, so we have this array, and this is the visual representation according to the question. Yeah. So we have to, let's say it rains some fine day, and we have to find the amount of water that can be stored in this configuration. Here, the dark blue things represent blocks, and the light blue things are the water units. So, for example, in this configuration, we can see that it has 6 units of water: 1, 2, 3, 4, 5, and 6. Um, is the question clear? We will share the attendance. I'll share the attendance form QR again later in the session. You need not worry too much about that. Okay, I assume everything is clear in the question. So, okay, what do you think you should do? You're given 2 pointers. I'll give you a hint. Even we have to keep track of the maximum and the minimum element that we have encountered from the right and left of our pointers. And you have to think in terms of barriers, because for water to be enclosed in a unit, you need to have barriers on either side. Difference of K. Hmm. What is K? Okay. Okay, let's just look at what we can do. We take 2 pointers L and R and initialize it to start at end of the array. Start. Uh, Hello. Hello. Am I audible? Hello. Just a second. Sorry for the mishap. Just give me a second. I'll be back. Okay. Am I audible now? Hello. Okay. Right. We take 2 pointers. We take 2 pointers L and R and initialize them to start and end the array. And then we take 2 more variables which keep track of the maximum element we have encountered till the left, till the pointer L, and till the pointer R, not including L and R obviously. And we iterate till L is less than equal to R. Okay, so this is the general idea. Let's see what we can actually do. Like what are the condition checks that we have to do. Okay, so condition one. So basically there are two conditions. Either left max is less than equal to right max, or left max is greater than right max, right? There can't be any other condition there. So we consider the element at index L. We have initialized L to be 0 and R to be um, the length minus 1 initially, left max to be 0 and right max to be 0. And yeah, we traverse until L is less than equal to R. So as we have traversed all the elements until the pointer L, we know the left max till the pointer L. Let's just consider the first condition that left max is less than equal to right max. Uh, and yeah, so we know every element that is the maximum element that we have until the pointer L, right? And as left max is less than equal to right max, we know that whatever the left max that we have here, is always going to be less than the right max that we have beyond the pointer R somewhere here. I'll explain this with an example, but let's just look at what we have to do. So these 2 points, they're just mathematical. They don't play much of a role, but yeah, I'll just read them out for you. For the right max of array L, we can say right max would be always greater than equal to current right max here, right? Because after this element L, every element that is succeeding this L would be at least the maximum of all the elements succeeding this pointer L would be at least greater than or equal to the current right max that is beyond the pointer R. So minimum of left max and right max at this pointer L would always be equal to left max. And as for water to get stored in a container, you need a barrier. You need something on two sides so that water can be stored within it. So we know that right max is greater than left max here, and we know the element index in the element here. And as we have a definitive point, a definitive, uh, let's say, condition that right max is at least going to be this value. So all we are concerned about is left max and the current value because left max is less than right max. So we just take maximum of 0 and left max minus array index L. Because why are we doing this? Maximum of 0 and left max minus array index L. Any ideas? Why do we have to take maximum of 0 and this condition? Think of it in terms of barriers. Like you need a barriers on both the sides for water to get stored. Uh, as we are running out of time, I'll just explain it anyway. Because that is because uh, if the left max is less than the element that we are on, that we are on at the left pointer L, then that means water would just overflow and there would be no water stored here. Let's take an example for this case at the index 2. Uh, I've written down the indices in the bottom. So let's take L is 2 and R is, let's say, here at index 7. This might not be the case that would show up when iterating through this array, but let's just look at this for illustration purposes. So everything, so the maximum element that we have encountered to the left of this index at the index 2 is 1 because this is the maximum that we have encountered until this index, right? And we are at index 7. The right pointer is at index 7. And the maximum that we have encountered until index 7 from the right is 2 again. Is that clear? Yeah. So as we know that there is a barrier of length 2, there is at least a barrier of length 2 succeeding this element L. We can be sure that any element, any length of water that might be stored at this position has to have a barrier of length 2. So there must be a barrier of length 2 succeeding the cell. So we are only concerned about left max because left max is less than equal to right max here. And here as left max is 1, we take maximum of 0 and left max. And here that comes out to be minus 1. As our left pointer is here, left max is 1, that is here, minus 1. That would mean water would just overflow over this block because water cannot be stored here. I'm sorry. Oh, okay. Yeah, water cannot be stored here because it will just overflow. Let's look at a case where water can actually be stored. Let's say L is at index 3. So obviously left max would be at index 2. That is 2. And let's take R, the pointer R to be at index 7. So left max is 2. Left max is less than equal to right max yet again. And the element at index L is 1. So we take maximum of 0 and left max minus array index L. And that becomes 2 minus 1, that is 1. So 1 unit of water is stored here. Is that clear? And after we evaluate how many units of water is stored, we update our left max by comparing it with the previous value and the value that we have at element n. In this case, we'll be comparing it with maximum of 2, that is here, and the value of element here, that is 1. It will still be 2, so left max will be 2. Then we just increment the pointer L. The same logic works for the right max as well. You can just try it on a paper, do different examples, but yeah, it is pretty intuitive once you look at it in terms of a container and barriers that have to be encountered, that have to be satisfied for water to be stored in that container. Yeah, this just tells you that you update the left max by comparing it with the current value and increment ly1 so that we can go on with the next comparison. The second condition is essentially the same thing, but we are doing it to the right pointer. As we know that left max is greater than right max, we don't care about left max. We are just interested in the difference between right max and the current element and 0. We just take the maximum of it and add it to our stored water in this configuration. I assume that is clear. Okay, let's just move on with its implementation. So this is just a function which returns an integer, that is the stored water in this configuration. And as we are iterating while L is less than equal to R, if the maximum encountered, if the left max until L is less than equal to right max, then increment we just increment this difference. We just increment the maximum of this difference and 0, because water might overflow, water might not overflow. And if it is not overflown, then this will be the amount that is contained in that unit on that configuration. Then we update left max and just increment the left pointer. And otherwise, we just do the same thing, but on the right side of the array and decrement right pointer. And we just return the stored water that we get later on. Here, plus equal to means stored water is equal to stored water plus maximum of whatever this is, maximum function and maximum function of 0 and the difference that we are interested to find. Right. So this is the attendance form. I hope that it's working now. If not, you can just let me know in the chat box. And this is the feedback form. Please do share your feedback as it helps us make our upcoming sessions better, and we know what mistakes we are making. You have to fill the feedback form again, and attendance form, I think you are supposed to fill it. Just fill it either way. Yeah. Yeah. Just please fill all the 3 forms. I'll wait for about a minute or 2. And in the meanwhile, if anyone has doubts, I'll try to answer them. Well, we are running short of time, but I think I can wait for about a minute or 2. Okay, right. Looks like nobody has any doubts. It's been a pleasure teaching and talking to you. And thank you for your great responses. And this is Suraj signing off. Thank you.